In section 2.6, we're going to be discussing families of functions. We're going to do some analysis of graphs and learn how to find the transformation of a function and then sketch those. So let's first of all talk about what we mean by families of functions. So when you have sets of functions in which all of the function have some kind of parent function that is then transformed into another graph, then we call those a family of functions. And there are going to be several parent functions that we're going to want to talk about. And if we look, the first example we have is the graph of y equals x. The graph of y equals x, remember, looks like a line with a positive slope that goes through the origin. Now, if I were to take that graph and shift it maybe to the left, let's say a number of values or a number of units, or if I were to shift it to the right, some set of units, or maybe shift it up some units, or we might even change the steepness of it, and we might stretch it a certain amount so that we change the steepness of the graph. All of those graphs would be in what we call a family of functions. They all make up the family, and the graph of y equals the absolute, or y equals x, would be the parent function, because all of those other graphs are formed by just taking y equals x and doing something to it. Shift it, stretch it, compress it. And that's what we're going to focus on throughout this section. Let's first talk about the different types of transformations that we can perform on a graph. The first one we're going to look at is called a translation. And a translation is just a shift. And what happens is, what we do when we shift our graph is we don't change our shape or our orientation. So if we have a graph that has a positive slope, then our transformation, or our translation in that case, would be a graph that would also have the same slope. So look at this first graph we have sketched here, and let's say that that's the graph of y equals x. So this green graph that we've got going through the origin, let's say, would be the graph of y equals x. Well, if I were to then take that graph and then just shift it up one, we would get the blue graph that I'm drawing here, and that would be a translation because we just took it, we kept the slope the same, we just shifted it up one. So if our original graph is y equals x, then our shifted graph in this case would be y equals x plus 1 because we just shifted up 1. So if we have a function y equals f of x, then y equals f of x plus some constant, let's say d, is going to be a graph that gets shifted up some positive amount d. So whatever the value of d is, that's how much we're going to shift up. We also can do the same kind of thing by shifting down. Let's say we wanted to shift this graph down to, then our graph would look something like this, and our equation would be y equals x minus 2. So a function whose curve looks like f of x minus d would shift down d units. So if d happens to be 3, then you shift down 3. Now let's look at another type of translation, and that would be if we had a horizontal translation. So if we look at our first parent function, which we have drawn here in black, that is the graph of y equals x squared. And notice that in our red graph, we've translated our function 2 units to the left. Well, the equation in that case would be x plus 2 squared. And in our purple graph, we've translated to the right, and our equation for that would be x minus 2 squared. So again, as we just discussed, if we have y equals f of x, if we took y equals f of x minus c, where c is some constant, and in this case we would maybe raise it to the second power like we did here, then that would take our parent function, which is a parabola, and this is going to shift everything to the right c units. If we have y equals f of x plus c, then that's going to be a shift to the left c units. It's important that we notice that what happens is you're actually shifting in the opposite direction in which it appears you would shift. If it's a positive value, like here, you shift to the negative direction to the left. If it's a negative value, then you shift to the positive direction to the right. So you have to keep that straight when you're graphing your transformations. Now let's look at a graph that's a reflection. In a reflection, what you're going to do is you're going to flip your graph over some line. So in the picture we have drawn here, we're reflecting over the x-axis. And notice the difference between our two curves. Our original graph was the blue graph of y equals x squared. So if my original function is y equals f of x, then the graph of y equals negative f of x is going to be a reflection of your graph over or across the x-axis. Now let's look at a reflection over the y-axis. So if we look at our function, our original graph here, the function for that would be y equals the square root of x minus 2. And if I look at the equation for the second graph, I would see that it is y equals the square root of negative x minus 2. And the big change that we should see here is that we have replaced our x in our first equation with negative x in our second equation. So when we have the graph of y equals f of x, then if we replace all the x's with negative x, we get y equals f of negative x. Our graph is going to be the reflection over or across the y-axis. Now let's look at stretching our graph. So let's say we have this original graph, and let me kind of highlight it here in blue. So this is my original picture of f of x. Let's say that's the graph y equals x. Notice what's happened here. My point that was at 1, 1 has now moved to 1, 2. Notice that the y number now is twice as big. My point that was at negative 1 is now at negative 1, -2. And we still maintained our point at 0, 0. So what's happening is we are multiplying the y values by some value greater than 1, which is making our graph stretch. So if our original function was y equals f of x, then if you wanted to stretch that vertically, you would multiply it by, let's say, some a, where a is greater than 1. And we'll actually put the absolute value of a is greater than 1. If that number happens to be negative, it would reflect it over the x-axis also, but the a value is what's going to stretch it. So if I were to multiply that same equation, like y equals x, and graph y equals 3x, I would expect to see a dot at 0, 0, at 1, 3, at negative 1, -3, and so I'm going to see my graph gets much steeper, and I've stretched it vertically. Now, if we do a vertical compression, it's the same as a vertical stretch, except we are going to multiply by a number between 0 and 1. So again, let's say that this first graph, and we'll highlight it in red this time, is my graph y equals x. Well, notice this graph that was at 0, 1 is now, or at 1, 1, is now at 1 and then maybe a fourth. And then there's 2 1/2, 3 3/4. Let's say that that's what we're multiplying by. Then we would expect that this second graph here might be the equation y equals 1/4 x, because we are shrinking it down and compressing it so it's not as tall. So if we have the graph of y equals f of x, then y equals k times f of x, where k is something between 0 and 1, is going to give you a compression vertically of whatever your value of k